So at this point, we've seen a couple of different examples of this derivative calculation thing in action. So I wanted to take a look at a couple more. Again, hopefully by the time we're done here, you'll see why I've picked this particular collection of examples. Anyway, so this time around, we're starting off with, I guess maybe a little less complicated, but also more complicated in a different way. We've gone from having a quadratic polynomial to a cubic, x to the third, but we don't have any like sort of hanger-on plus, whatever term at the end. So just as a reminder, I'm going to change this h of x just to be clear so we don't end up mixing the function up with the h that shows up in the limit. That's, one of the tricks of doing something live like this, well, live-ish. Anyway, so p prime of x looks like the limit as h approaches 0 of this difference quotient thing, p of x plus h minus p of x all over h. All right, so now we just kind of fill in the blanks like we did before. In some ways, it's less complicated because we don't have quite so many terms in the top just yet. So we also don't need to worry about distributing that minus in the back because it's just minus x cubed. We don't have to worry about any parentheses. Now, the trick here is how to handle x plus h quantity cubed. My beloved FOIL algorithm kind of doesn't really extend to tell me how to handle a cube. It stops at squares. As you say, if you're used to using the grid approach, you've got kind of a way to expand this. You may also be familiar with something called Pascal's triangle, which kind of will help you blow these things out relatively rapidly. In any case, however you get at it, here's what you should end up with. If I can fit it all. Yeah, I'm almost out of room here. I'm going to have to write kind of, awkward. But, so that's what's going to happen if you hammer out all of the calculations, combine like terms and stuff. You have x cubed plus 3x squared h plus 3x h squared. Again, note that the square moves there. Plus h cubed. And no, I have not forgotten that minus x cubed. I'm just not willing to write on my wall here. So, and the whole thing is over h. So hopefully that's clear. In any case, there's a lot of stuff here. Does it clean up? A little bit. X cubed minus x cubed. So that stuff's gone. Kind of like what we saw in that quadratic example in the previous video, though, it's actually even easier to see here because we're not having to mark stuff out of the middle. Those three terms that remain, every one of them has an h, right? So I'll come down here and factor an h off this thing. The first term, all I'm left with is 3x squared plus 3xh plus h cubed, all over h. Just like in that previous example, anywhere other than 0, we're safe to get rid of the h from the calculation, and we're left with this thing. And now we can do a direct substitution of 0 for, that's right, do it for h, don't do it for x. All right, so when we plug that in, I'm short on board space. I'm not going to write it out quite as carefully as I have previously. This thing, I'm going to plug h equals 0 into it. I plug h equals 0. That should be an h squared. I forgot to factor it off. I just wrote h cubed all over again. That should be an h squared right there. Yes, I did factor an h away from it. My bad. But still, if you're plugging 0 into this thing, 0 squared is the same thing as 0 squared. It's still nothing. It goes poof, just like the last one. So the formula for our derivative in this instance is simply 3x squared. The other terms go away when we do the direct substitution of h equals 0. All right. So now, if you take the time and write down some of our previous examples, you might end up noticing a bit of a pattern building here, but maybe not. In which case, let's take a look at one more example. All right. So now, instead of having a quadratic or a cubic, we've got the reciprocal function. f of x equals 1 over x. So to make sure I've got enough space for this, I'm not going to recopy that limit definition of this thing we call the derivative. You've seen it before. If you need to, hop back and grab it again. There's no harm in that. So we have the limit as h approaches 0 of the function value with our x replaced with x plus h. So we have 1 over x plus h minus 1 over x all over h. So we've got triple-decker fraction. So I know fractions are often scary for folks, and this is like even scarier. Now we've got fractions inside a fraction. What madness is this? It's mathness. It's not madness. But anyway, so how are we going to clean this thing up? It might be a bit tricky to recognize. So again, in the interest of conserving board space, I'm going to kind of do two things at once. One, I'm going to take this division by h and rewrite it a bit, just to clean this up. So remember, dividing by something is the same thing as multiplying by its reciprocal. So I'm going to put that 1 over h just in the back. Like, technically I could distribute it, but I don't want to, because before that, I want to come back to something that we did back in our pre-calc review. We have two rational expressions here. I want to put them together using a common denominator. So I'm just going to grab x plus h times x. There's not really anything simpler that I can think of. Anyway, so now inside here, multiply top and bottom of this guy by x, because I don't have an x term. So we have x minus, now I multiply top and bottom here by this denominator, x plus h. Again, note, I need those parentheses. I'm going to have to distribute that minus sign. I won't write the of x. We can keep that straight, although now you can still see the white marks where I got rid of it with my finger. Oh well. And at this stage, I'm going to go ahead and put the h down there, because you can multiply across, right? So denominator times denominator. There we go. So I've got, I'll put a multiplication dot in there. And I'll close up those parentheses, even though I technically don't need them. All right. So from here, now, again, it may not be immediately clear how this, straightens up, but you may notice x minus x. So those should, annihilate each other or make each other vanish. You get the idea. So up top, still need my limit. Like I said, I'm very careful about writing that guy down. I'd still have the negative, times this plus h. So I've got a minus h in the numerator, and I'm going to rewrite the bottom a bit. Remember, multiplication, commute, so I can flip the flop how I have those arranged, at will. That way, my h is they're sitting in that same spot. So we have h up top and an h down below. Spoosh, spoosh. They disappear. Now again, remember when I cancel that away up top, that leaves me with a 1 that's still got a negative on it. So I have a negative 1. So I have negative 1 up top, x times x plus h down below. Again, I can now do a direct substitution. Plugging in h equals 0 doesn't cause bad things to happen. So I have negative 1 over x squared. Again, notice there is a separation there. It's minus 1 over x squared. All right, so that's covered a fair number of these examples. Again, I could have gone back and done some applications where we played around with tangent line slopes and that sort of thing. We'll get to that. But for now, what I want to do is take what we've looked at so far and collate some data into like a chart. So yeah, you may notice that the marker that I've been using since the semester started, it's finally reaching the point where I couldn't actually read what I wrote here all that well. So moment of silence. Press F to pay respects. However you want to meme this. He's done for now. He's deserved his rest. Anyway. So on this side of my chart here, I've got all of the functions we've looked at. I rearranged them a bit. I liked having the square root a bit further down. But anyway, so x squared plus x, x cubed, square root of x, and now 1 over x. And I've got the derivatives listed over here. Now, if you'll permit me a moment, kind of imagine that plus sign is breaking these two guys in half, because you can see sort of a parallel that ends up running through these things when it's all said and done. So we have 2x, so we have x squared. We have 2x. If we don't have an exponent, that means it's, understood to be x to the first power, right? Same deal right here. So we have x squared became 2x in a sense. X to the first became just 1. Remember, 1 is kind of like the same thing as x to the 0. So you may see a bit of a pattern building if you look at those two guys. Then you look at the x cubed sitting underneath it. There's something kind of happening there. Does that apply to the square root of x? Well, maybe. We can write this as a fractional exponent, right? That's x to the 1/2 power. Then we have 1/2 times the square root of x. That's another x to the 1/2, but it's in the bottom. So we have like 1/2. Remember, the 2 doesn't hop up top when we change, the sign of our exponent. But we get 1/2 x to the negative 1/2 x. So again, maybe the pattern's continuing. You might see where this is going. That's x to the negative first. We come over here, we rewrite that, we get negative x to the negative second. Our data are indicating that we're kind of doing something consistently. In all of these cases, we've taken our exponent, it's kind of become like a coefficient out in front of these things. And then our exponent, after we had done this derivative calculation, dropped by 1. 2 to 1, 1 to 0, 3 to 2, 1/2 to negative 1/2, negative 1 to negative 2. It decreased again. So that's kind of food for thought. Before we bring this section to a close, though, I did want to take a look at something else about derivatives, but it's the kind of thing I want to be able to point at calculator pictures for, so look for another video on